Okay, thank you, Jason, for your wonderful presentation. Questions? Questions from the audience? I can start with one question.
Bob can't ask me a question because he wouldn't let me ask.
Do you want to? Jason, there are many students who are dealing with, in many labs here in Brazil, we have the chewing simulators. They are very popular here. And it's always a question of the frequency that we are using. We can set the load very easily within the range that you showed, but the frequency is always a question because we have the pressure of time to finish the thesis and all that. Mm-hmm. So the students are always trying to, use a higher frequency to get the same number of cycles faster. So how should we deal with that? Should we reduce the frequency and spend more time, or can we increase the frequency and do our experiments faster?
It depends on the class of material that you're testing. If your material is predominantly glassy, if you're testing a porcelain or glass ceramic material, those are probably not affected by frequency at all. They usually do not exhibit a cyclic degradation effect. And so then if you test at higher frequency, you will not accelerate the test. It will have no effect. So there's no reason to do that. However, if you're testing advanced ceramic, partially stabilized zirconia, although we don't use it yet in dentistry, a coarse-grained alumina material would also exhibit a frequency effect. Or if you're testing metals, there will be a frequency effect. In those cases, you can conduct the test more rapidly by increasing the frequency, as long as you use the general log linear model to compensate for that interaction, and as long as when you do the failure analysis, you do not see what Bob did on the implant specimens. You do not see a change in the mode of crack propagation.
Is the log linear coefficient analysis in Alta 7?
Yes,
Pro?
Yes, it is.
Okay. I would love to ask your opinion about the practice that you see commonly in Europe, especially, that other people around the world are starting to follow, where they'll have a chewing simulator that goes to maybe 50 newtons or 20 newtons or 100 newtons, and they'll let it chew on things for 20,000 times, and then they'll load it monotonically and look for damage accumulation and think that they're somehow simulating a fatigue failure. What's your comment on that?
I tried to do that with Alta Pro software. I tried to model a fast fracture group and also model a fatigue group and somehow relate the two analyses. And I found out that when you do a fatigue test and you ask the software to go into a cumulative damage mode and convert from that to predicting a fast fracture, it could not predict anything at all.
Yeah, I would add that I would suspect that if you look at the failure mechanism, it's going to be whatever you see in monotonic, maybe starting with a little larger flaw. It's not going to reflect necessarily the damage accumulation you see in real fatigue conditions.
I mean, there are reasons to do that type of experiment. For example, we're about to start, my grad student Graf is about to start an experiment where he fatigues cracks in zirconia. He starts some specimens with a large flaw after regeneration treatment, and then other specimens he starts with a small flaw, and he fatigues them to grow the size to see and then fast fractures both groups of specimens to see what type of residual stress we have at the crack tip. But that's a fracture mechanics experiment. That is not useful to predict fatigue lifetime.
Right.
Yeah.
If we accelerate the tests, like for ceramics, let's say 500,000 cycles at 20 hertz. You spend like 7 hours to test one specimen. In this period of time, do you believe we have enough time to have the effect of slow crack growth or not?
Yes, I think that you will have slow crack growth. Usually, if you fatigue the specimen and you're fatiguing it at a certain load amplitude, then at that load amplitude there is some critical flaw size that will cause failure. A specimen will not fail until the flaw reaches that size. So if you have to get it there by changing the frequency, then that is one way to do it, but that should not affect whether you will always see the subcritical crack growth, because the specimen will not fail until you reach the proper size of critical flaw. And you only have to do fractography afterwards to make sure that what you're seeing looks like the clinical case, that you have not really changed the failure mode, that you have only made it happen faster. And again, if you're dealing with these glass matrix ceramics, then probably you won't see much acceleration by using the fast frequency. Take the same amount of time to fail if only stress corrosion is causing subcritical crack growth, then it's only the amount of time that it's up at the high point of the loading curve. And if it's up there twice as often, that doesn't change the amount of total time.
Professor Jason, I would like to know your opinion about evaluating lifetime, recording the number of cycles until failure. Do you think is that useful? Can we get useful information doing that?
Oh yes, I would record the frequency and the number of cycles till failure. That way you cannot be certain whether frequency is having an effect or not until you do the data analysis, right? And so if you record the number of cycles to failure and the frequency, then in case there is no frequency effect, well, then you can put those two together and you have the lifetime, the number of seconds, the number of hours. So yeah, you should definitely record everything until you analyze the data.
Okay, thanks.
Anything from your cell phone, from the internet, or did I put them all to sleep over there?
No, not now. Okay, so thank you, Jason, very much. And now we go to our last presentation.